Welcome back and welcome to week 2. Today I'm going to kick things off with something that I may occasionally do, something that I like to do in person at least to get people thinking about soils related concepts. So I may, no promises, but may throw in some of these occasionally in my lectures. But this is a photo of soil. And the questions I'm asking you about this soil are, what do you notice and what do you wonder? So take a minute, take it in, think about it. We've got a scale bar over here in feet, so this is actually quite a deep soil. What do you see? What do you notice and what do you wonder? A couple things, now that you've had a chance to think about it a little bit, that I'm going to point out. We've got all of these little lines down in this zone, right? Those are stratifications from sediment deposits. We've had little bits of sediment being stacked up, and this is probably, based on that and one other feature I'll show you, probably in a floodplain. So we've got occasional floods and a little bit of sediment spills out onto this landscape and settles out of the water, and then the next time it floods you get another layer, and so we get these little thin deposits. And it's taking hundreds of years to stack up that much material, but in terms of soil development, that's not super long, and so this is a pretty young soil. This material, you can still make out all those lines. What horizon would you call that? It's a great example of a sea layer. Down below you see this dark zone, and that is an A, which you might wonder, wait, how could that be an A? Is an A at the surface? And we'll talk a little later about some extra letters that we can add that provide additional information, these sub-designations. The little B that would go on here means it's buried. So this used to be an existing soil. It moved into the floodplain and got buried by these sediment deposits. So that dark layer used to be at the surface, but now it's been buried by all of this sea material. So just an example of how we might start to apply some of the terminology we've used and think about that, what that tells us about how the soil has developed. I'm going to give you a couple reminders today. Last week I walked you through the assignment in the video. You have those instructions. You can ask questions if things are unclear, and so I'm not going to do a full walkthrough of that assignment. But I'm going to give you the reminder at this point. You're going to have some lab videos this week that will help along with that. But just as a reminder, and we will gradually expect you to become more and more self-reliant and remember to do your weekly assignments and your weekly quizzes, but I am reminding you at least this week. We're in week 2, we're still figuring things out, so just don't forget. Your assignment is due on Wednesday. Your quiz is due on Friday. So last week we talked about the components of soils. We talked about those components impacting properties and functions. We talked about the development of soil profiles. Hopefully that all sounds familiar. Go back and skim through your notes if you're a little hazy on any of that. Today we're going to talk about weathering, physical weathering, chemical weathering, and then we're going to think about soil forming processes that are in part built upon those weathering processes. So we will start with the general definition of weathering. It's a chemical or physical alteration. We're changing things. We're thinking specifically about mineral materials, rocks and minerals. We're breaking them down, we're transforming them, we're doing something with them to change them. I like to think of it as minerals in search of equilibrium with surface conditions. If you think about a grain of quartz in a granite rock, that quartz developed under high pressures and super high temperatures deep underground in a magma chamber as it cooled off very slowly. Those conditions are very far from surface conditions. We've got much lower pressure, much lower temperatures, and a whole lot more water and more oxygen, and so it's a different environment. And because these minerals are exposed to a different environment than where they formed, they're no longer in equilibrium. So they're in search. I'm anthropomorphizing our minerals a little bit here. But they are out of equilibrium with surface conditions, and so they're going to change in response to those surface conditions. We'll start with physical weathering. Physical weathering, we're not changing the chemistry, right? That'll be for chemical weathering. But physical weathering, we're just breaking it into smaller pieces. It's still quartz, but now it's smaller pieces of quartz, or whatever mineral you started with. We're not transforming it, we're just breaking it into smaller components. And there are a bunch of ways that physical weathering happens. Temperature fluctuations. You heat something up, it expands a little bit, you cool it off, it contracts, and it's small changes in volume, but when you're dealing with a rock, something very brittle and hard and solid, those little changes in volume can start to loosen things up and cause them to fall apart. Fire, that is kind of taking the temperature swings to the extreme, but if you really heat up a rock to 600 degrees or something and then cool it back down, then that's a more dramatic temperature change. Freezing, again, temperature change, but in this case, let's throw a little water in the mix, and if we get some water in a crack, this photo up in the top here is an example of all of these things operating, but particularly in this high cold environment, water gets into these cracks, and that freezing causes a much greater expansion. As that ice freezes, it expands and pushes things open, and then more water can get into the cracks and then push them even more the next time it freezes. Salt crystals, similar to ice crystals forming and expanding and pushing things around a little bit. If you get salt crystals, that's actually what has happened in this photo over here. These little pockets started with little salt crystals developing in this rock. Root pressure. Here's a great example of that. My driveway is another great example of that. At some point we're going to need to resurface because we've got roots going underneath that are pushing things up, and the roots, as they grow, they can exert a lot of pressure and split open a rock. And then release of overburden. This is one that you might think of a little less, but if a rock was formed deep underground, kilometers down, it's got a lot of rock on top of that. That's a lot of weight and a lot of pressure. If it gets uplifted and the overlying material is eroded away, that overburden is removed, then suddenly there's a lot less pressure and it kind of expands just a little bit. The pressure is released, and so it changes volume, and that can lead to physical weathering. When we weather physically, we are creating smaller pieces, meaning we're creating more surface area and more porosity, and that allows for more weathering reactions and soil forming reactions to take place. Reactions happen on surfaces. As we create more surfaces, we get more processes happening. And some of those might be chemical weathering reactions. So here we're actually changing the chemical composition. Maybe we're rearranging, maybe we're not adding or removing any atoms, but we're rearranging them into different components. Or maybe we are we're adding O2, or we're adding H2O. We're actually changing the molecular composition, the structural, at the atomic scale, we're changing that composition of the rock or mineral. We're forming new minerals, or we're destroying old ones. By definition, if you're changing the chemistry, you're changing your minerals. You're either getting rid of some or you're creating new, and usually it's kind of a combination. We alter one into something else. Hot and humid climates speed this up. We're going to talk about climate a little later this week, but high temperatures and water allow for faster chemical reactions to take place. And most chemical weathering processes in soil specifically are promoted by carbonic acid. So carbonic acid, the chemical formula here, don't be scared, I know we haven't gotten into much chemistry yet, we're not going to get too complicated just now, but this is an important thing to understand. This is carbonic acid, H2CO3. And you can separate off one of those hydrogens, and that hydrogen can then go react with other stuff. It's an acid, and as you maybe intuitively know, acids cause chemical reactions. So the question is, how do we get carbonic acid in the soil? The answer is through this reaction. Water plus carbon dioxide. We've got 2 H's, we've got 1 C, we've got 3 O's. Water plus carbon dioxide makes carbonic acid. That is a hugely, hugely important reaction to understand for soils. How do we get water in soils? Not too hard to imagine, I think, unless you're in a very arid environment. In extreme desert, there's water in the atmosphere. We get precipitation, rain and snow, and so water, check. That is pretty common in soils. How do we get carbon dioxide in soils? I mean, there's a tiny bit in the atmosphere. If you go back to last week, think about soil atmosphere. Carbon dioxide is much more abundant in soils because of microbial respiration. All those microbes, billions of them underground, are breathing, releasing carbon dioxide, enriching the soil atmosphere in carbon dioxide, and so we have more carbon dioxide in the soil, we have more carbonic acid. We are constantly producing this carbonic acid. It's a weak acid. It's not going to dissolve your hand if you stick your hand in soil, but we have just a slightly acidic environment that is naturally produced in most soils through these just very common constituents. So, important reaction to understand: water plus carbon dioxide produces carbonic acid. Carbonic acid produces a lot of our chemical weathering reactions. The other point I want to make here, there's a positive feedback between chemical and physical weathering, right? I mentioned physical weathering produces surfaces, more and more surface area. That's where the chemistry happens, and then as you undergo these chemical reactions, it often weakens the mineral structure of your starting material, which means then a little physical weathering can actually do more to break it down into smaller pieces. So it weakens our rocks and minerals, so they break down more. The more they break down, the more surfaces where chemical reactions can take place. So there's this natural feedback between the two styles of weathering. We're going to talk about a few more specific varieties of chemical weathering. The first one is hydrolysis. Hydrolysis literally means hydro, water, lysis means splitting. There are, depending on your field, you've maybe come across things where you lyse molecules or something. It means to split. And so hydrolysis is splitting water. And basically, we are using the hydrogen off of H2O, one of those hydrogens, to attack a mineral structure. This is somewhat complicated to read it all on the screen here, but basically we've got a little carbonic acid in this water droplet, right? We have hydrogens produced from that weak acid, and that reacts with, in this case, a feldspar. When we hit that feldspar, oops, back to my pen tool here. When we hit that feldspar with a little hydrogen, a little acid, hydronium ions technically, that will lead to alterations. And this is a little bit of a black box error, right? There's more going on to get from this point to that point. But what we've done is this hydrogen came from up here. We've added hydrogen to the structure because we've split water. In this case, it was carbonic acid that we kind of split earlier on. But that acid has attacked the mineral structure and formed a totally new mineral. In this case, we went from feldspar to a clay called kaolinite. Then there are other things left over in solution, and that starts a lot of other processes. But that hydrogen ion attacking silicates, transforming them into other minerals, is a big change in soils and an important one. It's often a really big modification in the primary minerals. We're going from one type of mineral to something very, very different, and a lot of those are clay minerals. We talked about clay as being really small, the smallest particle size in our mineral soil material, but it also has some specific chemistry that we'll get into later in the quarter. This is how we produce a lot of our clays, through hydrolysis. Our next type of reaction is dissolution. And dissolution is a little less complicated, one you're probably more familiar with. If you pour table salt into a glass of water, the salt dissolves. That's dissolution. In soils, salts are present in some soils, and so that's one of our dissolution reactions. The other really important one is carbonates. And carbonates are things like limestone, or calcite is the mineral name. They are not really soluble in water. If you put a block of limestone into a cup of water, come back in a week, it'll still be there. It doesn't dissolve very quickly. But they are soluble in acids. So if you somehow could imagine just a little bit of acid in your soil environment, I don't know where it would come from, other than microbial respiration, producing CO2, combining with water makes carbonic acid. That might be one path. If you get an acid source, right, then suddenly carbonates become soluble and they will start to dissolve. So here's some salt. That'll dissolve. This is some limestone, and you can see, especially along these seams, these are areas where water is getting in, and that water with just a little bit of acidity starts to cause dissolution. Our next reaction is related to that dissolution of calcite, of calcium carbonate or limestone, and that is carbonation. And so this is basically, the simple version is we're reacting minerals with carbonic acid. So a lot of these seem kind of familiar or related. The carbonic acid is a common theme here, right? We're getting a little bit of acid here. Here's that reaction I wrote out for you a few minutes ago. We've got carbonic acid from microbial respiration, right? Microbes give us that. We get that from the climate. We get a little acid. If we take limestone and carbonic acid, we can produce calcium bicarbonate, which then can break down into ionic components. So this is an example of both a dissolution and a carbonation reaction. Not all dissolution happens in the same with carbonic acid, but if we're reacting things with carbonic acid and producing these carbonates or bicarbonate ions, then that is a carbonation reaction. So this one kind of fits both. Not all, they don't always overlap, but it's a common example that works both ways. Oxidation. So oxidation, if you think back to your intro chemistry, oxidation, Leo says grr, lose electrons, oxidation, right? Or maybe you do oil rig, oxidation is loss. Whatever the mnemonic is you remember to remember oxidation, we're losing electrons. So for example, we go from iron with 2 plus, Fe2 plus, or ferrous iron, to Fe3 plus, or ferric iron. The charge number is getting bigger, but we're becoming less negative, right? We're losing electrons. And so even though it looks like it's getting bigger, it's actually from a loss of an electron. If we start with a primary mineral, this example, it's pyroxene. That's something that you might find in basalt. Most rocks, especially like, think about an igneous rock that's cooling in a magma chamber underground, there's not a lot of oxygen in that magma chamber, and so most iron in primary minerals, the starting minerals in the rock, are reduced. They don't have the oxygen that's pulling away electrons. When you bring them up to Earth's surface, suddenly we've got 21% oxygen in our atmosphere, right? Maybe a little less in the soil, but a lot of oxygen that wasn't there when they formed, and they're out of balance. And that oxygen can react with your iron, pull off that electron, cause oxidation, and then we get Fe3 plus. And if we do a little more processing there, another reaction with some water present, we produce Fe2O3, which is an iron oxide hematite. That's basically rust, is a form of hematite. And so that transforms our iron, right? The iron itself is totally different, but we've also, by reacting with this iron, we've pulled it out of the mineral, and the mineral loses stability, right? We've pulled out this iron, or even if we don't pull it out directly, it's changed its charge, and the mineral becomes a little unstable and is subject to other reactions. So if you see red in soil, that's a pretty good indication that we've had some oxidation taking place. The flip side, right, is reduction. Leo says GERD, gain electrons, reduction. Oil rig, reduction is gain. We've gained an electron. And that usually happens after oxidation. So we have this oxidized ferric iron. If we add an electron, then we go back to Fe2+, to ferrous iron. That happens when we saturate the soil with water. In this photo you can see the water down at the base, right, and this whole zone through here at least some part of the year is wet. It gets saturated, the oxygen is gone, there are still other processes happening, microbes that are trying to make a living and start passing electrons around, and they use iron as their electron acceptor because oxygen's not available, and we reduce that iron. Reduced iron is mobile. Fe3+, it gets tied up with oxygen and it's stuck. It's not going anywhere. But Fe2+, it is free to move around within the soil. So it can be relocated, it can be lost from the soil altogether. And this process, the graying of the soil, because we go from this red oxidized iron to this basically colorless reduced iron, we get kind of these gray colors. And if we remove the iron altogether, we just have kind of the white of the quartz or other minerals left behind. If we have the iron present, sometimes it has a tiny bit of a bluish tinge to it, or a green. You can kind of see that down in this zone maybe, that it's just slightly blue from the presence of reduced iron that has been transformed in the soil by reduction and then moved around. If we combine those two, we go back and forth, which is common near a water table, because water tables rise and fall seasonally. When it's wet, they come up, dries off, they drop. And there's a zone where it's wet some of the year, dry some of the year, and we often get what we call redox features that are kind of these splotchy looking, some zones where we've concentrated iron in the red to yellow to orange zones, right? We're concentrating iron. And other areas where the iron has been removed when it was mobile as Fe2+. So we have these zones. These are called depletions because we've depleted the iron out of them and concentrated them into the concentration. So these kind of mottled looking splotchy grays with oranges tell us that we have fluctuating water tables through this area. Sometimes it's reduced, sometimes it's oxidized. So to not draw out the video too long, I'm going to throw in some review questions. They are in your slides. I'm not going to talk through all of them. I think you have the tools to go check it out, but this is a chance for you to do your own understanding check on some of these. So take a look at some of these on your own time. Well, it's all on your own time, but so this video doesn't get too lengthy. Here's another one. Central Africa. Which process do you think is going to be dominant? Chemical or physical weathering? This is one that there's some nuance there. So there's more than you just, oh, here's the one obvious question answer. Another review question, make sure you've got a handle on this. How does physical weathering increase the rate of chemical weathering? Another question. I'm not even going to read this. Check the slides, and we will pick up from there in the next video.